Thank you very much, and welcome to Vicenza. You cannot imagine the future if you do not know your past. And the past started when we treated the first soldiers wounded during the Korean War with the rotating drum kidney. This is Paul Techan in 1956. And you can imagine how complicated and hard it was to treat those patients. We started actually in 1977 after the Göttingen experiment by Peter Kramer to treat the first patient on continuous arteriovenous hemofiltration. And as you can see, there was an artery and vein connected through lines to a highly permeable filter. This led to more and significant interaction between renal medicine and ICU medicine into a new specialty that actually we call critical care nephrology, and we well defined this early in the 90s when Rinaldo and I met and started to work together. This was the first symposium we did in the 80s. You can see Dr. Ronco very young here with hairs and less kilos. And here is the same group of pioneers meeting several years later. And many of these people are not with us anymore, unfortunately. This also led to development of books on acute kidney injury and blood purification in intensive care. And from the moment we started with the continuous arteriovenous hemofiltration, we moved towards attempts to develop a fluid balance system, and then adoptive technology with pumps and veno-venous approach. Subsequently, new machines, and the first machine specifically designed for renal replacement therapy in intensive care, the Prisma. And then, of course, the second and third generation of machine with more characteristics and more features, possibility to support different organs, and finally, even using this for what we call ECOS, which is extracorporeal organ support. And now we have the fourth generation of machines for CRRT. The vascular access will be next talk. At that time was complicated because you had to puncture an artery and vein or use a Scribner shunt. The ultrafiltration negative pressure was just generated by gravity. For the younger people, this can be incredible, but this was the way it was working at the bedside. And also the filters we had were not completely perfect because they were used for pumped circulation. So filtration pressure equilibrium was occurring inside the filter, and the clotting was made easier by this problem. So we developed a series of different prototypes and filters that were used in different patients depending on different blood pressures and the possibility to achieve different blood flows in the extracorporeal circuit. Also, flat dialyzers were designed for arteriovenous hemofiltration. This was called a simple method for fluid balance. You can see from the computer how old I am. And of course, anyway, this was a way to collect information. Several fluid balance were developed by gravity, like the Equaline, or by gravity and pumps. And one of the most interesting advances was the addition of diffusion to the convective therapy originally designed. This was the first patient ever treated with arteriovenous hemodiafiltration in the world, where fluid was circulated by gravity countercurrent to blood in the system. Very soon we started using double lumen catheters and machines that were motivated by the chronic hemodialysis, and blood pump and reinfusion pumps started to be used, allowing us to develop different forms of techniques that are today a normal characteristic for any type of machine. As I mentioned, the Prisma was the first machine designed specifically to be used in intensive care, especially because it had this feature of the pre-assembled circuit that allowed a self-priming in the system. And then, of course, we moved to second and third generation machines. As you can see here, the prototypes had different colors compared to what you're used to see, but this is the progenitor of the Prismaflex machine, and this is the most recent Prismax machine, for example. Also, other companies like B. Brown started from adoptive technology, the EcoCarX system that we developed in Vicenza that led to the development of the Diapact machine. And this is the prototype for the Omni machine that was originally designed in California. And this is the final machine that is in place today. Also, Fresenius designed different original machines and finally came up with a very sophisticated CRRT machine called Multifiltrate first and Multifiltrate Pro subsequently. So this is actually a kind of evolution that we have seen over the years, having now platforms capable of doing different type of therapies. And in fact, in critical illness and sepsis, what we need often is what we call multiple organ support therapy. And therefore, different machines are capable of supporting different organs. But the same evolution we have seen in the adult, we have seen in neonates. This was the first neonate ever treated with continuous arteriovenous hemofiltration in Vicenza in 1982 with the mini filter that we designed. And here is the evolution with the search of a mini filter, then new membrane design, specific mini filters and mini circuit for neonates and treatment. And then CVVHD and ECMO developed for neonates. The adaptation of Prisma for these patients, and subsequently we started a project to reduce the priming volume of the circuit and miniaturize a machine called Carpe Diem. We designed the new project, and finally in 2013 we came to the first patient ever treated with this miniaturized device called Carpe Diem, which I designed originally. You can see that I'm not a good designer, but basically everything is there. And this was the first baby ever treated in the world with this machine. We also tried to put together the opinions of different companies in order to achieve an harmonization of terminology in different machines, calling different therapies and actions with the same name. So this was called Nomenclature Standardization Initiative. And we have two papers in critical care that summarize this nomenclature approach. Several books have been published, but the most important advance was probably the creation of a consensus group called ADKI that started in New York in the year 2000. And this was the first paper that we published ever. We did a meeting here in Vicenza in 2002 where the final resolution was the creation of RIFLE. And I think this has been one of the major advances in our approach to AKI. And in fact, the paper that we published was a paper that has been the number one paper in critical care for many years, and I think still is. ADKI met several times. Here, all the ADKI members are taking a cappuccino with me, and we have been discussing several issues, including the importance of technology and precision medicine, starting from assessment of risk down to clinical diagnosis, indication, identification of targets, and then finally prescription, delivery, and monitoring of the therapy. Today we can actually accumulate and save a lot of information from different treatments due to information communication technology systems, both in cards, medical records, or clouds. And we can actually analyze this data that become a very big database in terms of quality indicators, filter life, treatment downtime, and so on, or even use this for specific trials, understanding what has been the criteria to initiate the therapy, what is the frequency of renal replacement therapy after CRRT, and so on and so on. What would be the future? Probably system to identify better the patient, optimizing CRRT, using therapies for extracorporeal support, and integrated equipment. For the patient identification, I think that we need to go into genotype and phenotype characterization, and finally leading to personalized prescription and precision medicine. CRRT technology is susceptible to improvements in different areas, from circuitry to anticoagulation to monitoring and biofeedback. And extracorporeal circuits may actually be designed with anti-thrombogenic surfaces, antimicrobial properties, temperature self-adjusting, maybe collapsible or biodegradable, becoming kind of environmentally friendly devices. We also may have developed development in fluid balance control, new membranes, sorbent devices, even wearable devices, and population-specific therapies. And all these different technologies may actually be integrated, like we have tried to integrate, for example, bioimpedance with blood volume measurement that we do in the chronic patient. We need to do this in the acute patient to identify better what the response to fluid removal will be in this patient. New membranes may be designed with specific porosity, and probably nanotechnology can help us to identify specific targets for molecules to be removed, designing not only a better inner surface at the blood membrane interface, but also kind of a pore library that allow you to design what we call today smart membranes. We can also functionalize the membranes on the surface, allowing specific interaction with blood and adding bioproperties to the membranes, as in the case, for example, of vitamin E coated membrane or other conditions. The effect on surface modification can be an improved in biocompatibility, permeability, non-fouling effect, and so on. Also, we need to design water-sparing technologies, what we call the blood planet dialysis, because water is one of the resources that is not freely available everywhere in our planet. The concept of biofeedback can be integrated into different signals coming from the lab, from the patient, from the machine, into a computer, and then finally generating an action in the machine that may be manually operated by the nurse, maybe authorized by the nurse, or maybe fully automatic directly by the machine. Today already we have some devices that are capable to modify the delivery of therapy based on monitoring what is happening, and in case of discrepancy between prescription and delivery, they are able to try to catch up downtime and other different things. I think that in sepsis, we may see in the future a kind of sequential approach. If infection, immunodysregulation, and organ damage are the different steps that we see in sepsis, probably our therapies should be somehow directed to all these different aspects. Source control, endotoxin removal at the beginning, then immunomodulation and cytokine removal later on, and multiple organ support therapy at the end. If this is the case, I think that different extracorporeal therapies may play an important role, from endotoxin removal, from cytokine and chemokine removals, and finally to support the failing organ. But we have to be careful, because in the use of extracorporeal support therapies, as we have native organ interaction, like cardiorenal syndrome, hepatorenal syndrome, and so on, we may have actually interaction between artificial organs, and different extracorporeal therapies may interact one to each other. So, for example, if you're using a VA ECMO and at the same time you are using a CPFA, you need to be aware of the possible interaction between anticoagulation, between fluid balance, and other possibilities. That's why in a recent paper we have somehow advocated the possibility to get an integrated hardware that in the future will be the single platform for any type of extracorporeal therapies. So this was a kind of 50 years in 5 minutes, but I think it's setting the stage for the whole meeting. As I mentioned at the beginning, you cannot imagine the future if you don't know the past. Thank you very much.